Hello, this is the first presentation on the work energy theorem chapter, and I shall have to go specifically slow in this chapter because this is going to be a very important foundational class. So let's just write here the work energy theorem. So there are many things that have to be presented in a very systematic manner in this chapter. So I would like to first state that we will start with discussing the work energy theorem for a particle. Okay, and sometime later we will try to see how we deal with this theorem for a system of particles. But I would urge you to postpone this for some time. Let's try to understand the work energy theorem in the context of a particle. First thing that we would like to address it is how does it arise? Before even we think of implications and the details of the calculation. So in my first presentation we'll ignore the implications of the work energy theorem and we'll ignore the details of the calculation. Instead, let's try to understand the question as to why did it arise. So I'll have to recap a bit and first state what is the problem for a particle mechanics. Okay, so one way that we have been used to this question is given the initial position, which I'm just calling it as position at time 0, and the initial velocity, find the position at every time and the velocity at every time. I just forgot to tell that you're also given the force history, the force on this particle as a function of time. So this is the way we have understood the problem in mechanics, and in particular to understand the significance of Newton's laws and their associated calculations. So once again I shall repeat the statement: given the force history as a function of time and the initial position and the initial velocity, we pose the question, what is x at all time and v at all time? And Newton's laws gives the following solution, which I shall now represent graphically. So you do know the force as a function of time, and it's like this. And then immediately Newton's laws tells us that some I'm talking about the particle, so force is equal to mass into acceleration at every instant of time. So this, what I have here, is acceleration as a function of time. Then let's say that this is 0. Then one focuses on finding this area under the curve, which is possible because we have acceleration as a function of time. So this area is equal to, between time 0 and t, is equal to, as we've studied, velocity at time t minus the initial velocity, which is known because we've written here that it's known, and this is what we want. And therefore, thanks to Newton's laws, which allows us to come from the force history to acceleration to velocity at any time. Now you could in principle plot velocity at every time, whatever it is, and write here velocity at every time. This is time. Let's say t is equal to 0, and once again find the area. This area from 0 to t on the vt graph is final position at t minus the initial position, and therefore in principle we have solved the problem. So this was the problem, and it's solved. However, there is a serious difficulty round the corner. So let's first state clearly what is it that's bothering us. What is bothering us is that f of t is not the way we get the force information in two very important problems, and I state one of them here up front, which is gravity. Gravity is a force which we can calculate only if we know the position of the particle. So here's a particle, let's call it M, and here's a planet M. The force of gravity, which is always attractive, depends on the position of the particle x, and therefore force is not a function of time but a function of the position. So this is a major difference, and this causes a problem which I shall explain a bit. But before that, let me state one more example which will play a big role in this chapter, is the force due to springs. So we know that if you have a spring with a spring constant k, and let's say this is the undeformed position, and the mass is in some position x, then the force depends on the extension x. In fact, it's as per the coordinate system, it's equal to minus kx. So once again, we have an example of a force whose value we get to know if you know the position of the object. And once again, let me repeat, force of gravity depends upon x, that is equal to 1 by g m1 m upon r square, where mass of earth, and this is the mass of the object. So here we go again. Maybe we can write r. So these are two important examples. Now, what is the issue? Why are we a little bit worried about the force information being provided in this form? And here's the simple answer. Let's say that I have a particle which is under the action of these two forces. So this is just some point in space, but let's say the space right now is planar, just to make things easy, and therefore this is some point on the blackboard or on this plane, and the object is going to move on this plane and reaches some point B. And the reason it reaches point B is because it's acted upon by forces. And the forces, these are the forces that are making the object move, and this could be a path. It obviously moves under does not violate Newton's laws. But now, what is the force as it moves along A to B? I'm unable to tell you, because if you want me to tell you what is the force here, I need to know its position. So I've given you examples where the force completely depends upon position. But a priori, I do not know the position. In fact, if you think about it a little bit, that's the problem. What is the position at different times as it moves from A to B? So the position at different times is unknown. That's the real unknown in the whole problem. And therefore, if you want to tell me the force in different positions, it's equivalent to asking the position. And that itself is the unknown. So the force itself is now unknown because the position is not known. So we do seem to have hit a roadblock in this particular problem where the force depends upon x, and we already have two important examples, gravity and springs. So here are two important problems, and we have a roadblock. Okay, and what is interesting is what will bail us out. What will bail us out of this seemingly unresolvable situation? Well, what will happen is, in particular, these two forces have a property, and we'll come back to the important property of these two forces in particular. And in fact, you might have already heard the names, so might as well mention it. They'll fall under a category of forces called conservative forces, okay, which will bail us out of this tough situation for us. But what we need to do is understand something else first, that while investigating this problem, we actually hit upon a theorem in mechanics that is not necessarily applicable only to conservative forces, but actually always true. Always true. Okay, so, and this theorem will become quite useful in the case of gravity and springs. So once again I highlight, what we're going to talk about is a theorem in mechanics that's always true, not necessarily in the context of conservative forces, but the theorem becomes even more powerful in the context of conservative forces, and will help resolve the enigma we are in right now. But that's for the later stage. First, let us fully understand the theorem and the fact that it's a theorem and it's always true, and in this form is it useful. Okay, so in the form in which we'll present the theorem, is it really useful? So we'll address that question first. So I'll just repeat it and highlight it so that you know clearly where we're going. So we're going to talk about something called the work energy theorem, which is always true and is a consequence of Newton's laws. So what we mean by the fact that it's a theorem is that it's not a law, it's a consequence of the law, consequence of Newton's laws for a particle. Maybe I highlight again that we are talking about a particle, and it's not a law, it's not a new law, it's a consequence of Newton's laws, and therefore there is a proof, and therefore it's always true. Now that is the first thing that needs to be clear, And then we ask a question, is this theorem useful? Is this theorem useful? And let me just tell you that it becomes particularly useful in the context of conservative forces, and we need to understand this slowly. But let's first understand that it's a consequence of Newton's laws, and let's also ask the question, which is always true, and let's ask the question, is it really useful? Okay, so why don't we get started? Now, when I say work energy theorem, let's take the simplest example first. Simplest example. Okay, so here we go. Let's say that there's an object moving in a straight line, and under the action of a constant force is constant. So this is clearly the simplest case. Okay, so the force is constant, and along the direction of the motion, let's say it's in this direction. Now we know that when it goes by a distance s, we do know that s is equal to, or let's write it like this, v square minus u square is equal to 2as. Mind you, force is constant, straight line, so a, magnitude a, is constant throughout the motion. So we can write this. This is one of the kinematic equations that are true when acceleration is constant. So let me continue with this writing. We know the special condition under which this is true. Now what we need to do is multiply by half m on both sides. And what you get is m into a into s. Mind you, this is a pure kinematic equation under constant acceleration, and this is just a restatement of the previous equation under constant acceleration. Now we'll use Newton's second law and call this force, and what we realize here is force into displacement is equal to final kinetic energy minus initial kinetic energy. So basically we've defined this as something called kinetic energy. Okay, so now this also we can call something. Let's just call it work in this example. So here we have a statement of the work energy theorem. So work, which is defined as force into displacement in this example, is equal to final kinetic energy minus initial kinetic energy. And better to write work done by the force external is equal to final kinetic energy minus initial kinetic energy, and this is the statement of the work energy theorem. Right? Now the question is, can we state it for the same kind of motion, but the force is no longer a constant force. Okay, now in this case also, now we have to be a little bit more careful. Let's say that the force is a function of the position. Okay, and now let's say the force was um, constant till here, F1, and here the force is F2. So in which case the work done will be defined as F1 x1, and this is x2. So F1 x1 plus F2 x2 will be equal to the final kinetic energy minus the initial kinetic energy. Okay, now this can be proved very easily, and in fact we can prove that just let me see if I can plot this as a function of x, this particular example that I've given. So this is 0, this is x1, this is x2. So the force was F1 from 0 to x1, and the force was x2, F1 from 0 to x1, and F2 from 0 to x2. Okay, so what we notice is this expression that has been defined as work on the left hand side. You can easily notice that it's the area under the fx curve, fx plot. Okay, so now I'm going to just state the work energy theorem for a straight line motion, and what we're going to say is that the work is equal to final kinetic energy minus the initial kinetic energy. And what is work? And I'm again assuming that the force is in the same direction that the object is moving, but with a slight difference, slightly more complicated, is that let's say this is x equal to 0. So as you move towards increasing x, the forces are going to change and need not be a constant anymore. So let's say that the force is variable, but now remember, force is a function of x, which is known, let's say. Now the work energy theorem states that this area is what we define as work, and if you manage to, so we can write it like this: area where the from x equal to 0 till x on the fx diagram is equal to final kinetic energy minus initial kinetic energy, and this can be proved. So I want to highlight the fact that I have not given you the proof for this, but can be proved. So what I mean by I'm not giving you proof for this is I did give you a proof for this one, and this is fine, very easy, but we made some fundamental assumption here that A is constant or F is equal to constant. Okay, so this is the only time we've actually proved it and said that the work energy theorem is a consequence of Newton's laws. And by the way, here's where we've used Newton's laws. Now making a statement that I can prove this theorem. What is the theorem? I'll state one last time in this particular video, and then I'll simply say that we have not proved it. Okay, but let me just state the theorem again. I know that an object is moved in a straight line. I know that an object is moved in a straight line, okay, under the action of a force F, and it moved, let's say, from x equal to 0 to some position x, and I happen to know the force history as a function of x, and I don't want it to be constant anymore. So this is x equal to 0, this is x, and this is force as a function of x. And then, since I know the force history, I'm able to calculate this area. This is my definition of work, calling it the area. And what I'm claiming, what I'm saying, stating the theorem is that this area from 0 to x is actually equal to the final kinetic energy, that's the kinetic energy at position x here, minus the initial kinetic energy, which is the kinetic energy at x equal to 0. Fine. Now I want to end this by saying that this is the statement of the theorem. Can be proved, this particular statement can be proved fairly easily. Just a little bit of calculus is required. Okay, and the proof just requires Newton's law. So in this particular context, we are saying that it's a theorem because it can be proved. It's a consequence of Newton's laws, and it's a theorem, and it can be proved with the help of Newton's laws. So with this, we have stated the work energy theorem for straight line motion, work energy theorem for straight line motion, and there are two cases here. Force is equal to constant and force is a function of x, and both cases and force is along the direction of the motion. In both cases, the proof is easy, and we have done the proof for force is equal to constant. We have not done the proof for a variable function, but believe me, it's easy. Now what we need to start thinking about is great theorem, okay, nice theorem, okay, but is it useful? Well, I'll just get on to the next video soon and address this question, but just putting some information up front. The answer is going to be like, it's useful under certain conditions. Okay, and the other thing, caveat that I'll state up front is, so what I mean by useful, it's powerful. Okay, but like I said upfront, let me state that it has a serious Achilles heel. Okay, there is a serious shortcoming, and so with this, I shall stop this particular lesson, and we'll get on to the next lesson very soon. See you. Bye.